Hi, welcome to this module. In the last module we have seen how to design how volatile organic compounds detection is important and how to fabricate a sensors for detecting such a compound. Now we will go in the detail of fabrication in the previous in the next few modules. But if you recall from previous modules from module 1 till now, we have seen several application of sensor. Now one more application of sensor is a flexible sensors. How where can we use flexible sensors? We can use flexible sensors at several applications including biomedical robotics. Alright. How about if I say that I want to know the change in the pressure of my wrist every time when I fist it like this. Whenever I make a fist, what is the change in the pressure of my in this particular area, which is my wrist area, right. I open it, I close it, I open it, I close it. Doing that, if I want to fabricate, if I have a fabricated flexible sensor, I can quickly understand what is the pressure that I am releasing and I am making a fist, what is the change. But you cannot use if I want to know all the way around, like all 360 degree, I should know the pressure, not only one side. Either I can use many sensors or I can use one flexible sensor which has a array of sensors. Same way there are a lot of applications, I am just helping you guys. We will see how to fabricate this flexible sensor. If you see the screen, there is one kind of sensors that we have which has not only a strain gauge. So, if you see the sensors that we are discussing here, right, that you can see here, these are like 1, 2, 3, 4, 5, 6, 7 and 8 sensors are there. Okay. So, there are 8 strain gauges. What do I mean by strain gauges? Strain gauges are a piezo resistor that are doped with the help of boron doping, right. So, this is a strain gauge. If I apply if there is a strain, there will be change in resistance, alright. If there is a strain, then there will be change in resistance. So, there is a strain gauge. On the strain gauge there is an insulating material, on insulating material there is a gold pad, on insulating material there is a gold pad, alright. So, if I want to fabricate it, it will look like this. But where is the sensor here? Sensor is right in the center of this particular device. That is why it is micro sensor, it is a micro sensor, right. And then you can see that the contact to the micro sensor, we have used some zigzag pattern like this, right. What is the reason of using zigzag and not like straight lines? The reason is that now it will have a less stress when the material is flexed. When the material is flexed, there will be less stress and thus the contact will not get broken, it will not get damaged. We will see how to fabricate this. Another application is to understand the weight of a fly. Now, this is a micro fly, this is a micro sensor which is capable of measuring the weight of a house fly. House fly we see every day, right, at several places, and housefly itself has lot of sensors, but we are not interested in understanding the anatomy of this particular insect. What we are understanding, we are interested is, can we fabricate a micro sensor that is able to measure the weight of a housefly? That is our interest, right. Can we fabricate a micro sensor that is on flexible material, right, or on the silicon substrate that can measure the weight of a housefly? So, how to fabricate such sensor, that is our interest, alright. So, until now we have seen lot of sensors. Now let us quickly see actuators. So since the course is on sensors and actuators, we should focus on both, but most of the time we will be looking at the sensor point of view. However, actuator is very important. It is a mechanism which that converts some type of energy into motion in order to work, right. Now, move a force over the distance, for example. And if you want to understand actuator, right, then in microengineering there are several kind of micro actuators. So, if you want to talk about remotely operated vehicle, right, then there are lot of application of actuators. Remotely operated vehicle is also called ROV, and the three common types of energy used in ROV work are electrical, hydraulic pressure or pneumatic pressure, while the most common actuators used in ROVs are motors, solenoid valves as well as pneumatic or hydraulics and or hydraulics. So, this is the application of the actuators. However, if you want to see from the overview point of view, then the overview, if you see the slide, then some of the common MEMS based actuators are piezoelectric actuators, thermal actuators and magnetic actuators. While other actuators can be the beams, it can be electrostatic actuators, it can be actuators and its mechanism. And when you want to use it, then the MEMS actuation options are piezoelectric based MEMS, thermally operated actuators, magnetically operated actuators, electrostatically operated actuators, while in terms of dynamics you can see the beam bending, damping, these are the dynamic systems. So, if I want to start with the piezoelectric or ferroelectrics, then the huge energy densities, it has good efficiency, a huge force can be measured, small displacement. The major fabrication challenge in terms of piezoelectrics is continuously promising technology. Okay. While if you know the piezoelectric effect, it is nothing but when you apply a force, there is a change in the voltage, right, and that is the piezoelectric effect, or a reverse way is when you apply a voltage, there is a change in the mechanical moment. So, what are the examples of piezo actuators or piezoelectric actuators? See, piezoresistive is different. Okay, when you apply a force, there is change in resistance is piezoresistor. Here, when you apply a pressure or force, there is a change in the voltage. All right. So, what are the actuator materials or piezoelectric materials? The first one is PVDF, which is polyvinyl polyvinylidene fluoride. Second one is zinc oxide, which is ZNO or ZNO. Third one is lead zirconate titanate, which is PZT, and fourth one is PMNT and PMNPT. So, the most commonly used piezoelectric material when you want to fabricate a micro actuator is zinc oxide and PZTs. So, the one page summary we can write it down is that it carries high voltage and low current, approximately 100 volts per micrometer, no static current, and that is why it is an excellent insulator. The highest energy density of any MEMS actuators, but the large force and small displacement, typically very difficult to integrate with other materials and devices, and but still it is continuously promising material. Now, the another kind of actuators are thermal actuators, and in case of thermal actuators, it uses the thermal expansion for actuating very effective and high force output per unit area. The actuator translates in this direction. So, for example, the actuator will move in this particular direction depending on how the cold and hot arm are changing its temperature. So, when we apply a current input pad, then there is a displacement which causes the change in the there is a heating in the actuator which causes the change in the displacement or translates into a directional point of view. We can also have a cascaded thermal actuators for high force. If this is a single actuator, we can have an array of actuators which can generate a higher force compared to a single thermal actuator. If I talk about CMOS, which is complementary metal oxide semiconductor, then there is a work done by Shen, Algato, Hu Robinson, U Alberta, University of Alberta, where they have worked on thermal actuations in CMOS, and here the Joule's heating of beam leads to differential thermal expansion, changing the angle of the mirror. If you see, this is a mirror, right, and when there is a Joule's heating, the angle of the expansion, thermal expansion, because of the differential thermal expansion, the angle would change, and that would cause the change in the angle of the mirror. So, this is what thermal actuators had been studied, and if you want to have a comparison like the summary of the piezoelectric actuator versus summary of the thermal actuator, then in case of thermal actuator the advantage are easy process integration. However, there is a large forces, small displacement, need lever mechanism to trade off force for displacement, which is the important point. Typically it is not so efficient like piezoelectric, and that is why it is inefficient. Time constants are approximately 1 millisecond. There is a substantial conduction through air, and there is a minimal convection in sub millimeter designs. The radiation loss is important about 300 degrees centigrade. There is a instant heating, slow cooling, except when radioactive losses dominate. So, these are some of the things that we need to understand when we are understanding the thermal actuator in detail. Alright. Now, let us see what exactly a MEMS are, because everything, whether it is actuator or a sensor, we have to use a technology called micro electromechanical systems based fabrication technology. And if you see the abstract of the MEMS reads like this, that the MEMS based technology consists of microelectronic elements, actuators, sensors, mechanical structures built onto a substrate. Now, most of the time the substrate is a silicon wafer. Further, the MEMS are developed using microfabrication techniques, that is deposition, patterning and etching. And the most common forms of production of MEMS are bulk micromachining and surface micromachining and HAR fabrication. The advantage or the benefit of the small scale integration brings the technology to vast number and variety of devices. We will be seeing some of the devices in the next few slides. Few examples are MEMS based micro pump, there is a MEMS based micro mirror device, MEMS headset display. What exactly MEMS are? So, the MEMS are made up of components between 1 to 100 micrometers in size. The devices vary from 1 micron up to several millimeter. Functional elements of MEMS are miniaturized structures, sensors, actuators and microelectronics. One of the main criteria of MEMS is that there are at least some elements that have mechanical functionality, whether or not they can move. So, this is the one of the main criteria when you want to study the MEMS. We will see the different applications. Right now, let us see, this is the last slide, which are the components. The components of the MEMS are microelectronics, microsensors, microactuators and microstructures. Right. You can see microelectronics, microstructures, microactuators and microsensors. So, when you talk about microsensors, microelectronics, then microelectronics is a brain that receives, process and makes decision. Data comes from the microsensor. When you talk about microsensor, then constantly its role is to constantly gather the data from the environment, pass data to microelectronics for processing, can monitor mechanical, thermal, biological and chemical changes. When we talk about actuators, then acts as a trigger to activate external device. Microelectronics will tell microactuator to activate the device. And finally, microstructures are extremely small structures built onto the surface of chip, built right into silicon of MEMS. Thus, if you see in a way, each of these 4 different components are interrelated, right, whether it is actuator, whether it is sensor, it is structures or it is a electronics, right. So, we will see in the next class the details, further details about the MEMS, how the fabrication processes are, and then we will start to see how you can fabricate the sensor. Before that, I want to teach you a very important topic called photolithography. Alright. So, till then you look at the lecture, look at the things that I have taught you. I will see you in the next class, and we will learn the further application of further details about the MEMS, followed by the PVD technique, CVD technique and lithography, right. So, I will see you in the next class. Till then you take care.